Welcome to the VEST webinar series. My name is Megan O'Neill, and I will be your moderator for today's webinar session. Today, we will demonstrate how to create assembly constraints and automatically assemble manifolds within MDTools. This webinar will last approximately 30 minutes. You'll be able to submit questions or comments at any time during the webinar by posting in the questions section located within your webinar control panel. Questions may be answered as they are posted, or we will try to address them in the last 5 minutes of the webinar. Note that today's session is being recorded and the audio is muted for all attendees. If you are experiencing any technical issues, please use the chat window to alert our support staff. Now it is my pleasure to introduce our speaker for today's webinar session, Carlo Molon. Carlo has worked in the hydraulics industry for many years and currently manages application sales and training for VEST desktop and cloud products. Carlo?
Thank you, Megan, and thank you, attendees, for joining today's webinar. So today we talk about assemblies, assembly constraints, and how to efficiently create assemblies using MDTools. While preparing for this webinar, I looked at the registrants and found the majority of you with Inventor. So I'm sorry for those using SolidWorks. Today, I will be using mainly Inventor. Most of the things that I'll show are common between the two platforms. There will be some technicalities today unique to Inventor. So I'll promise to make another webinar related just to SolidWorks, maybe in the next webinar sessions that we will have, probably spring next year, so that I cover also some particularities, because I see a lot of customers trying to start using assemblies, and I see a lot of room for improving. So let me start the introduction. I have prepared a set of 3D models, step files, which I'll instruct for assembly purpose, and then we'll see how to use them in a sample block. We'll focus today mainly on footprints, so surface mounted valves. The experience I have is that it's very easy to constrain components as a cartridge valves, and I'll show you in a minute how to do that. So if you are working with Inventor or SolidWorks, and you already have a 3D model in that platform, you just open and then apply the constraints. Since I'm now importing step files, I don't have the geometry now, so I will just do a 3D model import. This is a technique I recommend for those using Inventor. So it's better to import a step into a part, because if you open directly the step may be an assembly, and then suddenly you get an assembly files. Normally, when we want to assemble valves or components with MDTools, we want to treat them as single items. So it's better to have parts. This will simplify dramatically the management in the assembly. So let me take just a random cartridge valve. That's an Eaton valve. When you import, this is peculiar to Inventor. Use the convert model, because you want to have native geometries. In SolidWorks, it's slightly different, but not that much. So now that's our model. If you go to Inventor browser, and similarly it will be for SolidWorks, you will see all the bodies. Want to instruct a component, in this case it's a cartridge valve, we will need to go to the MDTools browser and click Set Assembly Constraint. These commands are valid also in assembly environment, and I'll show you later how to make a bolt kit to assemble on top of a slip-in cover. But now I'm using the same command within the part, which will be the most common scenario you will be using. So we have 4 options here. Today we will focus mainly on cartridge and valve pattern. We have also expander and orifice, which basically behaves the same. I'll show you an example of orifice plug shortly later. That's a cartridge valve. For cartridge valve, we need to select 3 different type of constraints. One is the top face, which is irrelevant for this type of cavity, because no components will be on top. So any top face I select is enough, is good. maybe just a top face, but really it's not a big problem which one. The bottom face is the mating face, the mating plane. So it will be the plane for the cavity, and I'll show you shortly. In this case, that's the standard cavity. It's a C10-3S Eton. So it's a slightly different version from the standard 7x8 for 14 UNF cavity, but we'll see it. And the axis is just the axis of the symmetry of this valve. When we are done, we click Set Constraint. As you can see on the left, 3 entities are created. When we click OK, we can just save as. We can save into our 3D library. My recommendation is, if you are creating a new library, create folders by manufacturer. So that will be my Eton IPT files. And I leave as IPT because next time I will create solid parts. So for the same application as SolidWorks. And here we need to save with a file name. Of course, we can put the same file name. Now I didn't copy it. Next time I'll do it. That was the CB Ctrl C. So I'll be using paste, save. If the same 3D model is applied to different components, then you can do a save as and change the name. So basically this information, the same geometry will apply to another component. If you need information for the bill of material, remember that the I properties for a part, this is particular to Inventor, but there is a similar structure in SolidWorks. There are project files, so you can type in pressure reducing valve, and the revision, the stock number, the part number, and it is possible to create custom properties. So when you populate this information, they will fall also in a bill of material if you create a bill of material with Inventor in this case. Similarly, it applies to SolidWorks as well. So every part that you save can have attributes, and you can create attributes and save attributes. If you have a PDM system, it will be probably easier to apply attributes from the PDM client, but now I'm working manually on each item. So that's easy for a part. A simple technique which will see the value in a different in the footprint, in the surface mounted, is this. If we just remove the bodies, this is particular to Inventor, so it is possible to leave the unresolved entities in the part, but as you can see, they are still there. So even if we remove a geometry, these entities are recognized by MDTools for the automatic assembly. So now if we consider it as a template, save as a cartridge Eton template, then we can just import the same valve for a different size. Well, maybe let me import the CBK. And if the 3D model has been made the same way, and as you can see now, the top face is there, but really it's not needed. The bottom face is the same. Then here we can just do a save as again and save with a new name, which is the K. So without wasting time in specifying again the constraint, we can reuse what we already had by importing a new geometry. So in this case, the bottom face is the mating plane. The top face is, in case of solenoid valves, is the plane where a coil will be assembled. So remember, the top face is relevant only for coils. And similarly, for a coil, you will put the same type of constraints, the top face and the bottom face. But this approach we will see mainly on the surface mounted valves, which we'll see now. Let me test this. So I'll start making a new block. And I'll build a small block. Let's make it 200 by 200 by 200. And let me place C10-3S cavity. I just call it reducing valve. Insert here and save it as my workspace. That's my webinar block. When I want to make a new assembly, I want to place in my assembly this block I have just made, which is my webinar block. If I want to assemble a cartridge to this cavity, I will need to go to MDTools 790, click on the components. Before doing that, make sure that you are in the MDTools assembly settings, you are pointed to the correct path. So I've changed my standard default path to this webinar path. So in my case, it's the 24 webinar, October webinar, 3D assembly, 3D file, 3D library. That's my path. So if I click component, MDTools will load the cavities available in this block, and I will be able to select a cavity and select a CAD model, go into my Eton, take my valve. Let me do something stupid. I put two of them, one on top of the other, and click assemble. MDTools will assemble one on top of the other using the bottom face of the second valve mated to the top face of the other. Of course, this is not a correct assembly, so I will need to remove the top one. But as you can see, you can understand the logic applied for mating valves one on top of the other. This will apply if it's a solenoid valve with the coil. This approach of cartridge style is valid also for sun style cavities. Sun hydraulics cavities I can show you in the MDTools library. We'll have not a spot face, but they will have a locating shoulder. So as you can see here, the locating shoulder is, let me take a screenshot so I can highlight it. Copy and put in a whiteboard. So my locating shoulder is this one. In the geometry, it is defined as step 2, and it's here. So basically, for sun style cavity, which are defined here, we need to take this as a bottom plane, bottom face. So if I take an example of sun valves, I will make a new part. And I'll import the CBCA LHN. And I can do the same assembly constraint, top face, bottom face, axis, set constraint. Okay. Now I can save it, save as, into my 3D assembly, 3D library, Sun IPT. And that's a CBCA LHN. If I want to test it, I go to my webinar block, search at T11A, counterbalance, place in my face, and go to the assembly. Now there will be a new cavity, which I can assemble by using the component. I take my CB, Sun APT, move to the right, and update all. And now I have all the components assembled. So there are two different advantages by doing that. First is that the assembly is made automatically by MDTools. So you don't need to work in the assembly. You don't need to apply constraints in the assembly. It is MDTools applying. So you once instruct the component in the part environment, and then it gets automatically assembled. The second benefit is that when we link through MDTools, if we do a common operation in a manifold design, like a change face, and we change face to a cavity, and maybe do connect to another cavity, and save. When we get back to the assembly, usually this is creating problem. If you do update, there are errors or build errors. which we can fix just by doing a component update all. Since we have tied a component to the cavity, now MDTools is able to rebuild and recreate constraints. We will use this technique in next MDTools webinar regarding a small design exercise. But now let's do a bit small step forward with the footprints. So basically, a footprint is describing a cavity made of different drills. So today I place 3 types of footprints. Well, 2 are enough. One is just the standard NG6 footprint. So I go to the direct control, it's the ISO 4401. Let me call it 1, and I put it on this face and rotate. And also I'll take a slip-in cavity, which is part of the ISO 7368. Let me take a NG25, and that's my NG25. And I insert here also. Let me change face to this cavity so that it's not disturbing. And also I change face to the other cavity. So basically, while it's very simple for a cartridge valve to be assembled because it's a cylindrical surface and we just need a mating plane and an axis. The problem of surface mounted valves is that they require an orientation. So let me create a small view so I explain the rules for assembling footprints, and then we do practically. I see a question regarding iParts. I'll jump to iParts quickly because it's part of my webinar. And that's basically the difference between SolidWorks. So let me show you, I put the views because I want to describe. So these are my footprints. I use a command which is a footprint, which is highlighting the envelope for the footprint. But I use another command called machining ID. I want to show the component ID basically. And let me take a screenshot for that. So for all the footprints in an MDTools library, it's independently on the shape, the size, it's applicable to all the footprints. To describe the orientation of the 3D model, you will need the axis. You will need an axis called BH1 and BH2. For all the footprints, since you need at least 2 bolt holes to assemble anything in a block, for this one, it's BH1 and BH2. So this is the locating pin. So BH1 is close to the locating pin and BH2 is there. For an NG6, that's the A port and that's the P port. So it's the axis opposite to the A port and 2. It may be different. That's my library. You have your standard MDTools library or a self-built MDTools library. Make sure you check what is the BH1 and BH2. So let me try to instruct the components for a DO3. I make a new part and import now 4W6. That's a Bosch Rexroth direction control valve. So if you remember my explanation, P, A, the axes which are opposite. So now the rule is set assembly constraint. It's a valve pattern. Top face is this. Bottom face here. First axis, second axis, set constraint. Okay. And now I can save it. Save as I go to my Bosch Rexroth IPT, and that's my 4WE6J EG24 and 9K4. Save. And if you need different one, you can save as. I want to build additional ones. I can delete this. Don't delete in the features. I can import another Z2FS. That's a flow regulator sandwich mounted on the same footprint. Let's show this. They are not in the correct position. That's not a problem. If you realize that the plane are not in the correct position, just redefine. Right-click, redefine, and touch the new face. Sorry, redefine, drag the face 0. Similarly, redefine, drag the face 0. And similarly, redefine, that's the BH1, and redefine BH2. And we can do a save as. That's a Z2FS, whatever it is. Let me copy the file name. Now that I have made this Z2FS, it will be probably easier because if I delete this body and import the other one, now I copy the file name before doing that. Usually manufacturers do things properly. They leave the same geometry, so I can do a save as and saving with this name. Then I can do again, delete and import again. So in this way, by using this technique, you really can quickly instruct several components fitting the same footprint. And now I save as and save and so on. Let's now test these components. And just for your information, I have built, but I'll show you shortly how to build that manually. I built also a bolt kit. So I'll show you now the bolt kit. The bolt kit is a assembly. Actually, it's an eye assembly. Yes, that's the, yes. So as you can see, this is my eye assembly, and it has several instances. Yes. Yes, I did something wrong in my. I'll show you in the new. I did change some file names, so I'll show you in the other exercise, doing it completely manually. Let me show you how to assemble it, and I create. I apologize for that, but I did clean up the file, and I should not have done that immediately. Let me do the assembly. I'll show you how to build from scratch that eye assembly. I want to assemble components on my DO3. I want to put my Z2FS, another one, my 4W6, and also my bolt kit. It will not work the way it should do, but I'll show you later an example how to make it work. Update all. Open. M5. Yes. It does not. Component. Let me add the bolt kit later to the other exercise. Update all. In this case, we are doing the assembly for all the sandwich model. Let me show you how to work with the eye parts and the eye assembly so that we make it work for this slipping valve. So I want to instruct the cover, the insert, and the bolts to be assembled to this geometry. So I'll start again with a new part. I import my cover. So from the step model, I import my LFA25. Now, if we remember that screenshot I took a few minutes ago, I need the axis next to the pin and the other axis. So in my case, a set assembly constraint, it's a valve pattern. I want the top face the bottom face, this axis and the second axis, set constraint. Okay. Now this I will save as into my Bosch Rexroth APT as LFA 25D7X. I keep the same template, removing the, well, I can import directly the insert. It's in the same position, so it's perfect. I can delete the previous geometry, keeping the features. Usually I move up my entities. In case of the insert, we need to make sure that the top face is exactly the correct one. So we just redefine the top face, redefine feature, and we take the top face, so that the next element is placed exactly on top of this face. Now we can save as LC25A and 20D7X. That's my insert. Now I want to make the bolts. So I have a generic 3D model for a bolt. Let me open it. It's in my C drive. So I show you now how to work with iParts and iAssembly in a better way than what you have seen earlier. I take an M12 by 40. So that's a bolt I have taken from, I think, the content center. You can have it the way you want. It's better if it is parameterized because we want to make it change the length according to what we want. So first I turn into an iPart. So I create an iPart. The iPart, I just needed the length so I can get rid of all the not needed parameters. Just the length. What I need is, maybe I just need the 40 millimeter and the member. So here you could add additional properties. So like a description, if you want to change the description, this information will then fall into the bill of material of inventor. Let me create new instances of that. Insert row, insert row, insert row, insert row. So I want to have the M12 by 50, M12 by 60, and 12 by 70, and 12 by 80. And you could put the part numbers. Now I copy the same one, but really it's not important. Of course, I'm doing quickly. Now what is important is to change the length so that this will change according to our need. So with one part, we can create several configurations. Let me click OK. And I want to save my part here. I want to do a save as into my 3D assembly, 3D library, bolts. That will be my ISO M12. And save. So this is an iPart. So an iPart has a possibility to change configuration. So as you can see, when you change the instance, in this case, it's just changing the length. So now, since a cover will have 4 of these bolts, I want to build an assembly, which is not a standard assembly. I want to build an I assembly. So I make a new assembly. In this assembly, I want to place my bolt. Okay. Now I want to ground this bolt, so I don't want it to be able to move anywhere in the. There are 4 bolts. If you don't remember the distance, you can go to the library or you can make a machining drawing or you can look at the catalog. But in my case, I'm just looking in the library. So the distance between bolts is 29 by 2, 58. So I'll do a pattern of this on 2 directions. One is the X and it's 58. and the other is Z, and it's again 58. So that's my pattern. Those are my 4 bolts. Now I want to define the mating plane. The plane, the top face, the bottom face, the axis, and the other axis. I need to define this as MDTools constraints. So remember, we are in an assembly environment, MDTools 790. The dialog is different, but we have set assembly constraints. It's a val pattern. The top face is this, bottom face, first axis, and second axis. Set constraint, okay. Now we want to make it as an I part, as an I assembly. So we create an I assembly, manage, create I assembly. This dialog is slightly different. Well, it's very similar to the part. Let me resize it. Now we want to be able to select which bolt we need. So we move the table replace here. And we can call this member as 4 times this. And again, we can put the information that we want. Another very important aspect to make this work with MDTools is in the exclusion. You will need to go to the work feature. So we'll need to pass the assembly elements to the I assembly definition. So planes and axes must be part of the definition of the table in the I assembly authoring table. Now we can duplicate. We can copy and make it. I'm just pasting, as you can see in yellow, you cannot have the same name applied to different instances of an I assembly. So you need to specify different naming. We can put the same naming here. And now the important part, we need to define which is the instance we need of the bolt. And we click OK. Now we have created a I assembly definition using I parts. And we can save into our assembly, and we can call it GM25 bolt kit. Now I want to test into my assembly. So I will close everything here. That's my webinar block. So in my webinar block, I want to put the component in the NG25. I'm going to select my insert, my cover, and my bolt kit. And I can update all. Now, as you can see, I have all the elements. Let me put the transparency here. I have the cover, insert, and bolts. The bolts are not long enough, so it is possible to change in the table, change component. That's a 12 by 40. We can make it a 12 by 50. So that it will change automatically on the part. And similarly, it will have been working also for the other ones. Now, if you intend to make a bill of material, Inventor as a way to, in the bill of material, it could consider the bolt kit as a unique item. As you can see here, it's a bolt kit, but it has also a mode parts only, which you can enable, which will show the children in an assembly. So in this case, it will consider exactly the 4 bolts. So according to your needs, you can consider the bolt kit as a unique part number for your bill of material. Or in case you want single bolts, they are grouped automatically in Inventor bill of material commands, according to the style of bill of material you define in Inventor. I think we ran a bit longer than expected. Like I said, I'm sorry for those using SolidWorks. This last part of this demonstration has touched practical aspect of Inventor. I promise I'll do a SolidWorks dedicated webinar for assembly, where I'll try to do the same with, of course, the commands and possibility available in SolidWorks environment. If there are questions? I don't see any other questions. If you have, feel free to post them, and we will be able to reply also in the coming days. If not, thank you again for joining. I turn it over to Megan.
Thank you. So that's all the time we have today for any questions. I hope the iParts question was addressed appropriately. If there's any other questions, or if you'd like more elaboration on your question, please follow up via email at support@vestusa.com with questions and details, and we'll get back to you within 24 hours. Okay, and thank you again to Carlo for delivering today's webinar. We would be grateful if you could complete a short survey at the conclusion of today's webinar. Tomorrow you will receive an email containing a link to view a replay of today's session. Feel free to share this link with your colleagues. A link to view video segments from prior webinars will also be provided in that email. As you can see, we also have the webinar series posted on various social media channels. We invite you to follow these channels so you can receive the latest updates on upcoming webinars as well as product releases. Our next webinar will take place in 1 week, where we use reusable templates to streamline the manifold layout process. And thank you again for Carlo, and thank you to everyone attending today's session. Have a pleasant and safe day.